it's happening. It just hasn't. Oh, there we go. I think that should be it. So hopefully everyone can see me. Oh, this is loud. Oh, this is loud. Not off. Not sure what's happening there. It's gone on a bit of a feedback loop. But hello, everybody. Welcome. Apologies. It obviously registered something funny there, but you should be able to see me, and then you should in a second be able to see my screen. So hopefully you can see the periodic table. But welcome everybody to our third chemistry class, web class. How is everybody doing? How many people have we got here? Please feel free to say hi. It'd be great to see who's here. Oh, my periodic table was taking a while to appear. There we go. There it is. Oh, I recognise some names again. That's nice. Hello, everybody. Welcome back. That's really great to see everyone again. We've got a mature student. Lovely. Welcome. Welcome. This is our third class. So if you want to, you can go back and look at the previous classes on the YouTube page. They should be somewhere there. And if you haven't yet, please feel free to download the slides that go with this lesson so that you can keep up. You can write in as much as you want. You could have it on a tablet if you've got a tablet, anything like that. That would be great. But hello to everybody who is here. Please feel free to say hi. And throughout this session, it'd be really great to have you communicating. So any questions you've got, anything you don't understand, when I ask for answers, it'd be awesome if you wanted to have a go at communicating, because we really find that you get so much more out of these classes if you, the more you put in, the more you get out. So if you guys are interacting with us, then you'll get so much more out of these classes. So please feel free to say hi and tell us a bit about how you're doing. We'll just give it another 30 seconds and then we will get started, just so I can check that everything is looking all good. The link for the slides should be in the description. So if you want to download the slides, please do. But hello to everybody who is here. Really nice to see some names again. I can recognize quite a few names actually, which is really great. So hello to you guys, and welcome to those of you that are new as well. So this is our third chemistry web class. So we're looking at the periodic table today, something which is instrumental in understanding chemistry, but something which people find very hard to get their heads around. So hopefully by the end of this session, you guys are going to understand the periodic table a whole heap better, or a whole heap more, which will be awesome. So Snap Provides are the best. Thank you. Yes, they are great. I totally agree with that. They are great. Oh, glad that you're finding them useful as well. That's awesome. Okay, I think we should get started. So just before we get started, in the same way that we have before, we have got a little bit about me. So I am I'm the lead GCSE chemistry teacher. I am also teaching a little bit of A-level chemistry for Snap Provise. I've got a PGC in chemistry education from Oxford University, and I have been teaching since then, and I've actually been teaching A-level chemistry for the last 6 years. So really enjoy science, really enjoy chemistry. This is something I'm passionate about, which is useful. And don't forget as well that the reason we're doing these classes is because this is something we are starting up. We're going to be having some GCSE tutoring is going to be coming soon. So if you are interested, there are at least 4 classes a week of GCSE tuition, so lessons, drop-ins, etc. We're going to cover the full curriculum in all of the exam boards. You get our amazing high quality handouts so you can follow it along, do it again later, redo the exam questions later. All of that comes with it. Every time we do a lesson, it gets recorded and then put up on the website, so you have access to it for weeks to come, so you can use that again for revision to remind yourself what we went through. And there's also access to one-to-one support as well. So this is something which is coming soon. So if you're interested in that, please sign up to our mailing list, and you can do that by entering your email in this link. If you enter your email in the link, you'll also going to be put into a draw, so potentially you could win a SnapRevise tutoring account for the rest of the academic year, which would be amazing. So we've got 10 accounts to give away, so 10 lucky people are going to get access to a SnapRevise tutoring account for the rest of the year. So all you need to do is enter your email in the link, which has been in the chat as well. So please have a look for that. Pop your email in there and we can see, or hopefully, fingers crossed, you might get access to a free account. It also is going to be lots of information on there about when we're starting classes and all that sort of thing. Is this the, I'm sorry, we've had a couple of messages while I've been talking. I think some of them have been answered, which is great, but is this the last we do classes? No, it's not actually. We are going to be doing it for another couple of weeks. So you have got at least another, what's the date, 11th, another couple of weeks of classes. So we've got lots to enjoy, lots to make use of, which is good. So today's lesson then, we'll get started. Today's lesson, we are going to, hopefully by the end of it, we will understand how the periodic table is structured, understand what the position of an element in the periodic table tells us about its atomic structure, and understand how the periodic table has developed over time. So these are 3 key things that you take for granted when we're doing chemistry. But if you don't understand it, it makes doing lots more of the fundamentals of chemistry really difficult. So we're not going to look at the reactions of elements in the periodic table, and we're not going to look at forming ions, because that will be happening in later lessons. So just a reminder, welcome if you're the first time you are here. If not, just a reminder for you guys that the specifications are here for you to use. So if you know you're on the AQA exam board, have a quick read through the specification points here, because it tells you what we're going to cover, and you can keep an eye out for anything that you might struggle with. I'm just going to put a line through this bit because we're not looking at the chemical properties today. This one is also for AQA. And then if you're not an AQA, if you are actually OCR, then this is your specification, or from your specification. So again, you can keep an eye out for what it is that you need to know. You can use this. And I'm just going to get rid of those bits because that is something we're doing in later lessons, not today. And finally, Edexcel as well. We're not going to look at that today, or that today. We did the bottom one last week. So the slides, if you haven't got them, a link has just been put in the chat. So if you haven't got them and you want them so that you can write on them, then please download them. Otherwise, you can just follow along. You can type in the chat, interact with me as much as you can, as much as you'd like. Please feel free to say hi, and then we can, I'll try and answer as many of your questions as possible. So Callie has just asked, how do the specifications differ? Well, actually, with this basic stuff, there is very little that differs about them. They are all very similar. It's only when you get onto the harder content that some of them have different definitions that they prefer, or some do include some things and some don't include things. But with this basic stuff, the stuff at the beginning of GCSE chemistry, it's all almost identical. So in this case, they don't differ at all. Hopefully that answered your question. So guys, can you give me some definitions or some explanations? How would you describe an element? What is the atomic number of an element? And how do we know that atoms are neutral? I'd like you to type that in the chat. That'd be amazing. I want to see what you know, and then I can write it into our slides. So what is the definition of an element, or how would you describe an element? What's the atomic number? What do we describe atomic number as? What's the definition of that? And how do we know that atoms are neutral? What is it that means atoms are neutral? Lovely, we've got lots of answers coming in, which is amazing. Good, yes, lovely. An element is made of atoms of only one type of atom. Good. Nice. We can't break them down anymore. So an element, if they are all the same type of atom, they have to have the same number of protons. So an element is an atom or atoms. Actually, let's put atoms. Element is atoms with the same number of protons. And as I think lots of you have said, which is amazing, if they've got the same number of protons, they must have the same atomic number. And you guys have, atomic number. And you guys have told me that the definition of the atomic number, or what is the atomic number, it's the number of protons in an atom or an element. So really good. So that's our definition. We have to be very aware that the number of protons in an atom defines the element. If you've got an atom with 3 protons, it has to be lithium. If you've got an atom with 6 protons, it has to be oxygen. That's how we name them, basically. So that's really good. And why are atoms neutral? Really good, guys. We've got loads of answers. That's fantastic. Really good. So you guys have told me atoms are neutral because the number of protons or of positive protons equals the number of negative, number of negative electrons. Brill. Electrons. Fantastic. Well done, guys. Okay, so continuing on then, this is stuff we did last week and the week before. If we've got a sodium atom, we've got what can you tell me about this sodium atom? What information, just from this picture, what information can you get from this? What do you already know about a sodium atom? And also, can you remember from last week the definition of an isotope? On both of those things. What do you know? What can we use this image to talk about, or to describe about a sodium atom? Any information you think you can give me would be amazing. And then what is the definition of an isotope? Ah, nice one. So some of you are remembering from last week, or you already know, which is amazing. Good. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. We've got 11 protons, therefore, because it's a neutral atom. 11 electrons, 11 protons. We haven't... Yeah, good. So if our atomic number is... if our number of protons is 11, that means that's our atomic number. So our sodium, for example, has an atomic number of 11. Somebody, please, if you're asking me questions and I appear to be ignoring them, I'm not trying to, just feel free to pop them in the chat again, because I can obviously only see what's in front of me. Otherwise I've got to scroll back. So if you think that I've missed a question, please feel free to ask it again and I will try and see it. What else can you tell me? What do you know about the electron configuration of this sodium atom? What can you tell me here? And what else do I know about the electron configuration, or to do with the electrons? What can you tell me about sodium? Yeah, well done, Dee, that's brilliant. There is 1 electron on the outer shell. And how many? Oh, nice, we've got a electron configuration there as well. 2H1 is the electron configuration. And how many shells? 3 shells. Good, I've seen that as well. So we have got 3 shells. So we can learn a lot about a picture of a sodium atom, or we can understand a lot about a picture of a sodium atom. So we're going to think about going back the other way, back to our periodic table. And the definitions of an isotope, we've got a couple of really good ones, so well done for those of you that have remembered. It's atoms of the same element with the same, so if they've got the same element, they must have the same atomic number, but with different numbers of neutrons. Very nice. Well done to those of you that got that as well. Oh, I flicked forward too quickly. There we go. So part one then, learning. What we're doing now. Will there ever be an A-level revision video? There are A-level videos actually every Sunday. If you wanted to head on over to the YouTube channel, you can find out what's coming up. And there's also a backlog of old videos as well from previous weeks. So please feel free to head over and check that out if that's useful to you. So periodic table. What is displayed on the periodic table then, guys? What is it that we see on the periodic table? And then how, in our modern periodic table, how are our elements ordered? If you look across the periodic table, what is happening every time you move to a different element? How are our elements ordered? How have we put them in order? Yeah, lovely. Thank you, Amy. A-level chemistry is once a month. Yep. And then there's maths and physics and biology as well. Good. Really nice. Yeah, well done, guys. So our elements are what's on the periodic table. Elements are what we display on the periodic table. It's the periodic table of elements. And our elements are ordered by increasing, and we need to make sure we put increasing, otherwise you don't get a mark in the exam, increasing atomic number, i.e. number of protons. Number of protons. So if this is our sodium, we can get the same information that we got before from here. We've got these two numbers. Can anybody tell me what those two numbers are? This one is our atomic symbol. Symbol. What are those two numbers? And then this is just our name. Good, we've got atomic number and mass number, really good. Mass is the more massive number of the two. So this must be 23 is our atomic mass, or mass number, whoops. Mass number. And we know it must be the mass number because it's the number of protons plus the number of neutrons. So it has to be a bigger number than the atomic number, which is just the number of protons. Lovely. Please let me know if anybody has any questions about that. Otherwise, let's have a look at our periodic table. The periodic table is called the periodic table because of what? Why is it called the periodic table? Why has it got the word period in it? When do you guys at school potentially use the word period? And I don't mean in biology, I mean in terms of your timetable. Why is it called a period? What does that mean? Why is it called a periodic table? Now, this is quite a hard question. Yeah, good. So we put them in periods, and we'll have a look at what that means in a second. But the periodic table, the elements are arranged in periods, in repeating patterns, which occur at regular intervals. So our similar properties occur in the table at regular intervals, and that's where our period comes from. You guys might call a period like period 1, period 2, period 3 at school. And that's the same, you're saying that it's a repeating pattern of classes. So we've got lots here. What this line here, what's that there for in our periodic table? What does this line tell us? I think some of you, oh, bye Evan, lovely to see you again. See you next week. What do we know then about these guys? Yeah, good, well done. This is our metals and our non-metals. And if you ever aren't sure which one's which, pick one that you know. So do you know silver and gold? Are they metals or non-metals? Well, they're metals, aren't they? So we know that this side has got to be our metals, and therefore this side must be our non-metals. If you're ever not sure, pick a metal that you know. Copper as well. is one that you might recognize. So these ones, if you're not sure, find one that you know. Platinum's next to it and everything like that. You can always check. And a way that I always teach people to find that, if you're not sure on your periodic table where the line is, you start in this top corner, and it's a set of stairs. It looks like a staircase, doesn't it? And if you're ever not sure where a staircase is, you can always find it by falling down the staircase. So if you fall down the staircase first, then you're like, ah, this is where the staircase starts. So I've fallen down it, and then I go across, down, across, down, across, down, across, down. And that's how we work out where the staircase goes that divides our metals and our non-metals. So which one's which? We've got rows and columns. We've got groups and periods. Which is which? Rows and columns, groups and periods. Which is which? What do we think? Rows, columns, groups, periods. Which way do we go? Do noble gases react? No, they're very inert. They do eventually. You can force them to react, but they're very inert. They don't react very easily at all. So we say they are inert. They don't react. So what are we thinking, guys? Columns and rows. Which one's which? Which one is which? And I'll start numbering them. Oops, I've run out of space. That's 8. What do we reckon? Yeah, good. Well done, guys. So our columns are our groups and our rows are our periods. And does anybody know the name of these highlighted groups? I think we've heard one of them. What are these highlighted groups called? We've got the red group on the left-hand side, the green group, group number 7, and then the blue group, group number 8. What are their names? What are their names? Really good. Yeah, columns is groups, rows is period, and we've got our alkali metals. Group 1. We've got our noble gases. Group 8. And then we've got our halogens, group 7. Really good, guys. Halogens. Nice. Well done. Really good work. Okay, so what do these mean then? These groups and periods. So we've said groups are the columns and periods are the rows. Now it's always group down and it's always period across. The groups are the columns. So what do these tell us, or what information can we take from our group number, for example? What do they tell us? Oh, good. I can see some people have already got there. Yeah, what do they tell us? What information can they help us get about elements? Really good, guys. This is looking nice. So groups tell us the number of outer electrons in an element. So exactly as you guys said, the group have the same number of electrons in their outer shell. We sometimes call these valence electrons, but you don't have to remember that for GCSE. Groups have the same number of electrons in their outer shell, and it is the number, and it's equal to the group number. Group number. So alkali metals have how many outer electrons? Noble gases have how many outer electrons? I'll just flick back to this page. Alkali metals are in group 1, so how many outer electrons must they have? And I can't remember what I just asked you, noble gases, how many outer electrons do they have? Really nice. Well done, guys. Good. So our alkali metals have 1 electron. All of them, every single alkali metal has 1 electron in their outer shell. And all the noble gases have, double check, count your elements, your number, wrong way. Count your groups carefully. This end one is group 8. Group 8. So noble gases, if they're in group 8, they must have 8 in their outer shell. That's supposed to say group 1. There we go. So noble gases must have 8 electrons in their outer shell. Very nice, well done. Good. Can group 8 be called group 0? Yes, it sometimes is called group 0, because the idea being that group 8 is or that most elements are looking to have 8 electrons in their outer shell if they can. So the noble gases which do have 8 electrons in their outer shell, so they have a full outer shell, then you can also say they have no electrons in their outer shell, because they've got their outermost shell has no electrons in it. The next one down is full, it's got all 8. So yeah, they're sometimes called group 0, sometimes called group 8. Either would be fine in an exam. Lovely. So, and then rows, I think I've seen it on the chat, which is amazing. Our rows tell us the number of electron shells. So rows have the same number of electron shells. And this number equals the row number, or the period number, I should say, actually, shouldn't I? Period number. I should say periods as well, rather than rows. That's me being lazy. Periods have the same number of electron shells in them. And this is the period number. So let's do some checking of that. Just check we're all happy. Yeah, good. They've got the same number of shells depending on what period they're in. Good. So let's have a look at fluorine then. Fluorine is in this group, and it's in this period. So what can we learn about fluorine? What do we know about fluorine? How many electrons? What can you tell me about the electron configuration of fluorine? Of fluorine, sorry, not chlorine. Of fluorine, what do we know? And this we're looking group 1, period 1, period 2, period 3, period 4, period 5, period 6, and period 7. Don't forget that top period with hydrogen and helium, it is a period. So we must not forget to label that as period 1. Lovely. So we know it's got 2 shells because it's in period 2. So it has 2 electron shells. And in the outermost shell, really good, it's got 7 electrons in the outer shell. So if we were to draw that, just as I think you guys said, we're going to have, well, we should know, hopefully, that the first shell can only ever hold 2 electrons. So our first 2 electrons for fluorine go in the first shell, and then our outer shell must have 7 electrons. 1, 2, 3, 4, 5, 6, 7. And notice how I paired them separately and then together, because they like to sit apart if they can. So I kept them apart, paired them separately. I placed them separately and then paired them when I had to, because electrons prefer to stay apart, just to make sure that as few as possible were paired. But in this case, there have to be 3 lots of pairs and then 1 on its own. And then if you were to write the electron configuration, which I think some of you have in the chat, which is amazing, you have to, you could call it 2, 7. Do you need to know the electron configuration for GCSE? You do have to be able to draw electron configurations of elements, yes. You do. With SPD, no, that's A level. No, you just have to be able to draw it, as I've done there, and then write it as well. 2, 7. 2 in the first shell and 7 in the second shell. So we agree with our placement in the periodic table. There are 2 electron shells, first shell and second shell. And then in the outer shell, which is our second shell, there are 7 electrons. Would you lose mark if you did it differently? I doubt it, as in if you just spread all of your electrons around on the outer shell, like all 7 spread out, not at GCSE. I don't think you'd lose marks at GCSE. So don't worry too much about it. It's just good practice, because when you get to A level, it's good to understand that they like to go around in pairs, or that they like to be separate until they have to go around in pairs. Okie dokie, see you later. Lovely to see you. Right, let's keep going then. So if we think about this the other way, or think about this without drawing it, use the periodic table below to determine the atomic number of magnesium. So how are we going to work out what the atomic number of magnesium is using the periodic table? It's a hard one, this one. We've got to work backwards. Tell me all you know about magnesium and its electron configuration, and we'll see if we can work it out. What do we know about magnesium from the periodic table? So we've got, it's in group 2 and it's in period 3. So what can you tell me about magnesium? Good, it's got 2. Oh, double check your numbers. We've got to work it out. So if we're in group 2, there must be, well, actually, so we'll do electron shells first. If we're in period 3, then there must be 3 electron shells. And if we're in group 2, then there must be 2 outer shell electrons, which I think some of you said already, which is great. So then how many electrons must there be? Well, if we write out the electron configuration, we know that there must be 2 electrons in the outer shell, and there are 3 electron shells. So we've got 1, 2, 3 electron shells. What's the electron configuration for magnesium then? Our previous electron shells have to be full. So what is a full shell 1 and a full shell 2? How many electrons can fit in shell 1 and shell 2 when they're full? Really nice. Well done, guys. Yeah, it's got to be 2, 8, 2 for magnesium. Our first shell was full, so it's got its full 2 electrons in. Our second shell is full. It's got 8 electrons in, sorry. And our third shell is the one that's half full or partially filled, and that's got 2 outer shell electrons in it. We know that from group 2. So then total electrons must be 2 plus 8, 10 plus 2 is 12. So if it's an atom of magnesium, if there are 12 electrons, there must also be 12 protons. So our magnesium has an atomic number of 12. Whoops, can't spell number. Number of 12. It's hard, this one, but hopefully you're seeing that there's a really nice relationship between an element and the periodic table. Really good. Where's hydrogen? Sorry, what? Hydrogen is kind of a bit of an odd one. It's got 1 electron in its outer shell. It's got 1 electron in its only filled electron shell. So it should be in group 1, but because it's a bit of an oddball, some periodic tables have it in the middle. They have it kind of floating around because it doesn't quite obey all of our periodic table rules, which we're going to look at in a second. So if you see it floating around in the middle, it's still in group 1. It still has 1 electron in its outer shell, and it only has 1 shell. It's in row 1, period 1. So it only has 1 shell, which has got 1 electron in it, but it doesn't necessarily fit with our other rules, which we're going to look at now. Hopefully that answers your question. Okie dokie. So, looking then, how confident are we feeling? How does hydrogen exist without a full orbital if it has 1 electron? Because our elements can exist without full electrons, without full shells. As long as they've got a matching, they're stable and neutrally charged if they've got the same number of protons as they do electrons. So they're quite stable like that. It's just, it would be even better, they'd be even more stable if they had a full shell. And so hydrogen can exist on its own. It would prefer not to, but it can. It doesn't go around fighting elements. It is reactive though. Right, good. Thank you, guys. Lots of you have said, told me where you're at. Okay, we've got some that are less confident. That's absolutely fine. Please have a think if there are any questions I can answer that will help you to get your head around this. but otherwise keep asking questions. And I will try and answer things. And if we have time at the end, which we don't usually, but if we do, we can come back and look at some things. So let's just test that knowledge then. So lots of you said that you were feeling really confident. Let's have a look. The electronic structures of atoms from 3 different elements are shown. We've got element W, which is 281, element Y, which is 288, and element Z, which is 2881. Can you name, using the periodic table, which we've given you, what the elements are? What is W, Y, and Z? So again, we're looking at the electron configuration of these elements. How many electrons do they have in their outer shell? Therefore, which group are they in? How many shells do they have? And therefore, which period are they in? And then you can match up the two and find the elements. Can you have a go? Yeah, the trouble is you will be asked in an exam to talk about the groups and the periods. So if you remember them as columns and rows, you might get a bit stuck in an exam. You might not be sure what they're asking, or if they ask you to talk about it, they're going to be looking for you to say column and period. I've said it now, group and period, not column and row. So it is good if you can to try and remember that they are groups and periods. Lovely, guys. So we've got a good start here. So element W, we'll just have a look at that one. It's in group 1 because it's got 1 electron in the outer shell, and it's in period 3. 1, 2, 3. Let's write in 4 and 5 as well. It's in period 3, group 1. So that's got to be sodium. What about Y then, guys? Really good. So we've got nice. Well done. So we've got, it's in group 8 because there's 8 electrons in its outer shell for Y, and there are 3 shells. So group 8, but 3, period 3. Well done. It's got to be argon as well. So really good if you said that. And then our final one, group 1 again, but it's in period 4. So it has to be potassium. So really good if you saw that. That's your 3 marks, 1 each. So nice one if you saw that. That's really good. Next exam question then. Sodium and potassium are members of the alkali metals. Explain in terms of their electronic structures why both elements are placed in group 1 in the periodic table. So they've even given you a number. They've even told you where they are in the periodic table. So why are they both in group 1? In terms of their electron structure. Why are they both in group 1? Yeah, really good. Well done, Zara. Straight in there. And hopefully everyone can see exactly right. They both have 1 electron in their outer shell. Really good. And that means, yeah, good. That means they are going to be similarly reactive. They react very similar to each other. Good. Well done, guys. It seems as though lots of you are feeling a bit more confident about this, which is nice. So we are going to move on to the next bit, which is the development of the periodic table. So we've looked at what it's like, and now we need to look at how it has changed over the years. So you might have seen information about this before. They have the period, we didn't used to know about all the elements. We used to be very confused, actually. We used to think that there weren't very many. We hadn't managed to, when we didn't understand what atoms really were, we then also couldn't work out that they were different types of atoms. So the very first, or one of the very first periodic tables, was very simple. How did we, or did scientists at the time, arrange this periodic table? This is an example of a very basic periodic table. How was it arranged? Does anybody know? And therefore, what were the issues with this periodic table, with this version as a periodic table? Any issues that you can foresee or problems that scientists might have had with this as a periodic table? Interesting. So they're not actually arranged in order of atomic weight. They're arranged in atomic mass. They're arranged in order of atomic weight, because we didn't know what their atomic mass was, or their mass number, was we just literally did it on weight. So we collected an amount of an element that we knew how much we had, and we weighed it. And the heavier ones, so like iron and manganese and stuff, they went at the end of the periodic table. And the lighter ones, like hydrogen and lithium, they went at the beginning of the periodic table. So if they weighed a lot, they went at the end. If they didn't weigh very much, they went at the beginning. So we went on atomic weight. Then we also noticed that some of them reacted similarly. So they were grouped with elements that reacted similarly, or that had similar reactivities. And that way we knew which ones, or scientists thought they knew which ones were like each other, that behaved like each other. So what were the issues then with this? Well, hopefully you can see that there are so many missing. Yeah, so our table was really incomplete. Oops. Oh, my rubber's not working. There we go. So our table was incomplete. It didn't have enough elements in there. They had as many as they thought there were, but there were many missing. So that's one of the issues with the first periodic table. What about the grouping, though? I think someone has said they're not perfect. The arrangements are not perfect. So some elements were put in the wrong group. Were put in inappropriate groups. Now, scientists at the time thought they were doing the right thing, but it might be that this looks quite neat, and at the time they were like, it should look neat, so I'm going to squish that one into that group because that's where it has to go, and I'll squish that one into that group because that's where it has to go. But actually they should have listened to themselves and realized that that can't be right. If they don't actually fit there, then we shouldn't put them there. And then well done, good. The modern periodic table's got a lot more. But they talked about the octaves, the trios, triads, things like that. So they looked at things that reacted similarly. But then a couple of other scientists did make some developments, but our main one that we're looking at is Mendeleev. And I think I've seen his name in the chat a little bit already. How did he arrange his elements, and what were the key things about Mendeleev's periodic table? Does anybody know what was good about his periodic table? What changes did he make that actually were really good in order of helping us to get to the modern periodic table? Yeah, really good. So in this case, you can notice that there are possibly 3 elements there that are missing. There's 1 that's missing there. There's another 3 that are missing here. There's 1 here. So he was very aware that it wasn't complete. So he left gaps for undiscovered elements. And actually, at the time, he was ridiculed for this. Lots of scientists thought that he was being very rude, telling them that they didn't know what they were talking about, because he had decided there were new elements that people hadn't found yet. He thought lots of scientists thought he was very, that it was very rude of him to make those assumptions, because it was telling people that scientists weren't very good. But actually, he knew what he was doing. He knew that there must be elements that we haven't discovered yet, and very good as well. And anything else that we know. Now, one of the key things about the periodic table, about Mendeleev's periodic table, he has arranged them in order of atomic weight. Arranged in order of atomic weight again. Weight. But the keen-eyed among you will have noticed that actually, although if you go along, it looks like it's going up 1, 7, 9, 10, 12, 14, 16, etc. They're going up. The atomic weight is going up. However, it doesn't when you get to tellurium and iodine. Now, why is that? What's happened here? Why are tellurium iodine suddenly, it goes 122 to 128 and then on to 127, so it goes back down again. So what's happened here? What did Mendeleev do that was actually incredibly clever for him at the time? Good question, Callie. I will answer that in a second. Good, well done. So he had to swap tellurium and iodine. He swapped elements so that they were no longer in increasing atomic weight order. He swapped elements in some places so that they were no longer in increasing atomic weight order because they fit with the reactivity. So really good. Because this fit with their reactivities. With their reactivities. So iodine, you might recognize chlorine, bromine, and iodine. They're all halogens and they should be in the same group, which Mendeleev, fluorine, which Mendeleev did put them in. He recognized that they all reacted similarly. So iodine shouldn't go one place to the left where tellurium is, because otherwise it would be in the wrong group. It doesn't react similarly to the elements in that group. So it had to go in the bottom one. And it's only now that we order our periodic table the way we do that we've realized we can prove how correct he was. And he didn't know that at the time. He made an educated guess that it should be that way around based on their reactivities. So we had a question, what's the difference between atomic weight and atomic mass? Nothing really, technically. We used to call it atomic weight. It was measured slightly differently, I think. When we look at atomic mass or mass number, we are talking about how many particles there are, subatomic particles there are in the nucleus, so how many protons and neutrons there are. When they did it before, they actually were just looking at the weight of the atoms or the weight of a collection of the atoms. So he arranged it by atomic weight. We arranged it by atomic number or the number of protons. So they are, atomic weight and atomic mass are basically the same, but we don't call it atomic weight anymore. We call it atomic mass because we measure it slightly differently. It's the same, basically the same number, but we just we're a bit more specific about it, I could say. Good, very nice, guys. Okay, so final thing then, we've looked at the initial periodic table, we've looked at Mendeleev's big development in his periodic table, and then finally, the periodic table today. Just remind me, how do we organize our elements? And anybody got any ideas how many elements there are that we're sure exist? How many do you think there are? Yes, good. We arrange them in order of atomic number. And it's definitely atomic number, as in the number of protons. And this is because we're then, if we take into account isotopes, like we did last lesson, if we take into account isotopes and try and order it by atomic weight, if it throws things out, things move around a little bit and then it looks a bit odd and it messes up the table. So it makes much more sense for us to order it by atomic number. And as you can see, if we order it by atomic number, everything stays nice and in groups neatly. And Mendeleev was absolutely correct because tellurium and iodine should be that way around according to their atomic number. So he was absolutely correct to make that change. And exactly right, guys. Yeah, there are over 100 elements. There's actually currently, as we write this, unless anybody has made any amazing discoveries in the last half an hour, there are 118 elements. So we found loads more since Mendeleev's periodic table. So how are we doing then, guys? We haven't got much left to do, just a couple of exam questions, but how's everyone feeling about that, about the periodic table, the development of the periodic table, and those key phrases that we've been practicing or talking about that you need to be aware of? There are lots to be discovered. Yeah, you're right, there are loads. Yeah, Rishi, good question. Some elements are artificial, or at least we haven't proven them to exist for more than a couple of microseconds in a laboratory. But as long as I think there is a time period over which they have to be able to exist on their own in a laboratory, and if they meet that threshold, then we say that they exist. If they don't meet that threshold, then we say that they don't exist. So you're right, some of them are, or lots of them were theorized, but if they are counted as an element in the periodic table, they have been proved to at least exist for a microfraction of a second. So we can say they do exist. Okay, so a bit of a mixture, but that's absolutely fine. How do people just discover elements? Well, good question. We don't just discover elements nowadays, but there are people whose job it is dedicated to taking atoms, smashing them together, and seeing if they can make something out of it. So they, if you've heard of CERN in Switzerland or in Geneva, it's got a Large Hadron Collider, it's called, and people there work at firing atoms together and firing particles at each other, trying to squish them together to make other elements. Because when this happens, lots of exciting things happen. And so they analyze what happens when they fire these things together and see if it's made anything new and exciting. And if they think they have, then they can use that to try and make more, or they can also look at going back the other way, so using radioactive elements and seeing if they can split them up. So you can split big elements up, but the trouble is we've filled in all of the periodic table up to 118. So we're only really looking if we whether or not we can go any bigger than 118, or to see if we can prove the existence of any isotopes of any of our 118. So yeah, there are people's jobs. It's very exciting. Very exciting. So let's have a look at this exam question. Am I a scientist? I would class myself as a scientist 100%. Yes, I have a master's in chemistry. And I am a teacher. So yeah, definitely would count myself as a scientist. Anybody who's interested in the world, though, can count themselves as a scientist. I think as long as you keep asking questions, you're a scientist. So let's have a go at this question then. So John Newlands first began developing the idea of the periodic table of elements around 140 years ago. He jotted down the elements known at that time in order, starting with the lightest atoms, and then from here he arranged them into 7 groups as shown in figure 1. There are many differences between the groups in Newland's periodic table and those in the modern day table. Write down 3 of these differences, basing your comparisons up to the element calcium. So what can you see that's different in these groups, group 1, group 2, group 3, etc.? What can you see that's different to our periodic table? And you might need to have a copy of a periodic table in front of you because I'm not going to be able to flick back too quickly. Thanks, guys. Well done. I'll see you later. So what are we thinking? Anybody got any ideas? Good. Yeah, lovely. So there's 8 groups instead of 7. Oh, sorry, I should put 7 groups instead of 8. 7 groups instead of 8. And what can you tell me about those groups? Yeah, good. So chlorine and fluorine have moved to group 1 for some reason with hydrogen. So hydrogen is in a group 1 with fluorine and chlorine for some reason, but that's because he thought they reacted similarly, so he put them in a group together. The halogens are in group 1 instead of group 7, and anything? Yeah, definitely fewer elements. And also, yeah, so our period, we have, what about our period? So this top period's got loads of elements in it. but our modern periodic table had 2 elements. 1, 2, 3, 4, 5, 6, 7. There are 7 elements in the top period. Period 1 instead of 2. Instead of 2. Good. Lovely. So there's loads of differences there. Thank you very much. See you guys later. And the elements are in different orders. Good. So they're not arranged in the same order. They're very similar, but not arranged. These ones should be over here somewhere. Good. Well done, guys. Final exam question. Have we got time? No, let's move on, I think. So there's half a mark left if you want to have a go at that on your own. But hopefully now everybody is happy that they understand how the periodic table is structured, our modern periodic table. We can understand what the position of an element in a periodic table tells us about its atomic structure, and we can understand how the periodic table has developed over time. So if you've got any questions, please ask them. But otherwise, if you haven't, then please go and check out our other GCSE classes. We've got GCSE Physics on a Monday, Biology on a Tuesday, Maths on a Wednesday, and then we've of course got Chemistry on a Thursday. So if you're at all interested in any of those, please go and check them out because they are awesome. They're all at the same time of 5:30. So just in case you find it hard to keep track of time like I do, they're all at 5:30. So that makes life so much easier. And they're all, like I say, awesome. So please go and check those out. And also they have classes that were recorded in the previous weeks as well. So you can go check those out too and get a bit of extra revision in, which would be awesome. And then finally, please don't forget to enter the competition because it'd be awesome if you got a chance to win one of our 10 free accounts that we're giving away. So please make sure you pop your email in the link, which has been sent in the chat as well. So really, really good luck. But even if you don't win, that link is going to help you, or getting on our mailing list is going to help you keep up to date with everything that's happening at Snap Provides when we're going to hopefully get this GCSE tutoring out to you. But if I don't, if I don't see you, then I hope you see you next week. Please feel free to come back. Don't forget to check out the previous videos as well. Really good, really well done if you stuck with us for the whole class. That's really good. Periodic table is hard stuff. It's really difficult, and it's something that students find very hard to take in and get their head around because it's not quite as, explosions and fireworks and fun, but it's so fundamental to chemistry. If we can understand it, we can understand so much about what chemicals do and why they react and how they interact with each other. And that to me is what makes chemistry fascinating. So really well done if you've come, if you've stuck to the end of that. Well done. If you were struggling, please feel free to rewatch it, make your notes, download the slides which are available, and otherwise I hope everybody has a really lovely day, rest of the evening, rest of your week, and hopefully see you next week. If you have any questions, please chat. Please ask me questions in the chat. Otherwise, thank you so much. You've been awesome. Well done, guys. Thank you very much. Yeah, I've seen, so our GCSE classes are Monday to Thursday, and I'll just pop that back there. GCSE classes are Monday to Thursday, and then our A-level ones are on a Sunday, and they rotate around. So if you haven't, please go check those out. Please feel free to enter the competition. That would be awesome. And I hope to see you guys soon. Yeah, hopefully next week. See you next week. Well done, everybody. Thank you very much for coming. See you next time. Bye, guys. Well done. Well done, everybody. Really good. Well done. See you soon. Bye.